Thank you very much for the invitation to attend the symposium. Unfortunately, I'm going to have to use my computer over here. So those of you over there, I will try to make eye contact occasionally by looking around the pillars. It's a great pleasure for me. This is my second visit to Brazil. I went to Rio about 10 years ago. I was invited by the Brazilian Volleyball Federation to come and visit their training site, and I had a wonderful experience. And I've been here, this is my third day, and I think I've already eaten a week's worth of food in 3 days, so I must now slow down. What I would like to do today is talk to you about what we know about neural adaptations that take place during strength training. And what I hope to achieve is I hope that I can share with you one or two things that you find interesting, and I am sure that I will say at least one thing that you probably won't believe. So let me begin this story. Most of us, when we see such an image, we usually assume that this person is strong. And that is because we have this common experience that muscle strength is somehow related to the size of the muscle. And this is well founded in experimental measurements, where on this graph what we're looking at is the strength, the true strength of some muscles in the hind leg of a guinea pig that were measured by electrically stimulating the muscle on the x-axis and then estimating the strength based on the size on the y-axis. So what you can see for all of these muscles that are listed on this graph, there is a linear association between the measured strength and the strength estimated from the size of the muscle. And the slope of that line refers to a value called specific tension, which is how much force you can, per square unit area of muscle, can be achieved. So this is fairly well established, primarily based on measurements made directly on muscle in experimental animals. But when we look at such an image here, where we have two athletes, we could ask the question, which of these two athletes is stronger? Clearly the one on the left has bigger muscles, but does that mean that this person is stronger than the one on the right? The relative strength of these two athletes, of course, you realize, depends on how we measure strength. So muscle strength depends on two parameters, basically, the size of the muscle and the details of the activation signal sent from the nervous system. So in this schematic here, what we're showing is a cross-section through the brain, the spinal cord, and some muscles that are attached to a skeleton. If we perform a strength measurement, we have a person push against a measuring device, and that force that can be recorded depends on the size of the involved muscles and how well they have been activated by the signal sent from the nervous system. The significance of muscle activation, the second characteristic, increases with the complexity of the action used to measure strength. So if you perform a very simple exercise, such as an isometric contraction, under most circumstances, the peak force that you get largely depends on the size of the muscle. But if you have the person perform a strength task where there is movement involved, then the peak force that you record depends also on the activation characteristics that the muscle receives. In my talk today, I am going to discuss the significance of muscle activation. And I'm going to do this by posing 3 questions to talk briefly about. The first question is, how does muscle activation influence the force exerted by muscle? The second question, how much do changes in muscle activation contribute to strength gains? And thirdly, how can we change muscle activation? For each of these questions, I'm going to provide a few examples of results from the research literature that provide answers to these questions. So for the first question, how does muscle activation influence the force exerted by muscle? I'm going to tell you about 4 studies. The first one is going to indicate that muscle activation can limit the rate of increase in force during rapid contractions. It can be depressed during lengthening contractions. It can cause a decline in motor function without a loss in muscle strength. So let's go to the first example about the rate of increase. So this is a study in which the dorsiflexor muscles experienced a training program that involved rapid shortening contractions. And in this photograph, what you see here, this is the knee of the person, the ankle is down there, and the foot is attached to a force plate. And when the person contracts the dorsiflexor muscles here, the foot pulls up on the force plate, and the force that can be exerted on the force plate can be measured. And in this particular study, the subjects were asked to do submaximal contractions, but to do them as rapidly as possible. So in the literature, this is sometimes referred to as speed training. So here are some measurements that were made before and after 12 weeks of speed training. So here is the torque of the foot pulling up on the force plate. This is one trace before the 12 weeks of training. And here is the surface EMG signal over the tibialis anterior muscle. And then the second trace here is an example of a submaximal contraction as quickly as possible performed after 12 weeks of training. And what they measured in this study was how much force was achieved during these submaximal contractions, but most importantly, the slope of the increase in force, the rate of development in force during the rapid contractions. And clearly what you can see in these 2 examples, for the trace after the training, the slope is steeper. And indeed, when they had subjects perform many of these contractions before and after training, these are the results that were obtained. So this graph is showing on the x-axis the peak torque that was achieved during the submaximal contraction, and on the y-axis was the slope of the increase in torque, so the rate of change in torque. And all the data points down below here, these were contractions performed before the 12 weeks of training, and the data points up here are contractions performed after the 12 weeks of speed training. So what these data indicate is that there was a greater rate of increase in force during submaximal contractions that involved 12 weeks of training with rapid shortening contractions. And this effect emerged for forces that were greater than 20% of maximum. So on the y-axis there, where you see the 20% value, then the difference appeared for submaximal contractions that were greater than 20 up to about 80%. So this is an interesting experimental observation. You do a strength training study where you do speed training, and you can learn to make these contractions more quickly. So physiologists are obviously very curious as to how this can happen. Well, if there's any change in muscle force after some training intervention or exercise intervention, this has to be due to changes in the way in which the motor units have been activated. So the obvious way in which these investigators tried to explain this observation was to look at what happened to motor unit activity. So let me explain to you how these kinds of measurements are made. So in this diagram here, you see a section of the spinal cord and some motor neurons with their axons going out and innervating muscle fibers. If we insert a fine wire electrode into the muscle it's possible to detect the action potentials that are discharged by some of these motor neurons during voluntary contractions. And what is shown on this diagram is the person, and the black line shows that the person gradually increased force from a resting value up to some target level, and the electrode, indicated by this black line, was able to detect the action potentials discharged by 2 motor units. One motor unit, shown with the green tick marks, began discharging action potentials at a relatively low force, and the other motor unit, indicated with the blue tick marks, began discharging action potentials at a higher force. So these forces, when they begin discharging action potentials, is referred to as the recruitment threshold, and we know from many years of experiments that motor units with higher recruitment thresholds are bigger and stronger than those that are recruited at lower thresholds, and usually they are faster contracting. And in the literature, this is referred to as the size principle. So when you perform a voluntary contraction, the first recruited motor units are usually weaker and slower, and as you increase the force, then you activate larger and stronger motor units. So here are some motor unit recordings that were obtained before and after the speed training intervention. On the left, you see some measurements made before training, and on the right, measurements after training. The top trace shows the force during the torque, during a submaximal contraction. The second trace shows a series of action potentials from one motor unit, one out of many that were activated. And then on the bottom trace, labeled C, is the same trace as B, it's just the time scale is expanded. So if we look at the bottom trace, labeled C, on the left and on the right, we have a series of action potentials that have asterisks above them. These asterisks are the action potential discharged by the same motor unit. And what I want you to notice is that before training, look at the distance between the action potentials, the 4 action potentials discharged, and compare that with the distance between the action potentials on the right. When the action potentials get closer together, this means the motor neuron is generating the action potentials more quickly. So what these data indicate is that by measuring the discharge times of action potentials here, after speed training, these individuals were able to increase the rate at which motor neurons discharged action potentials. So during these rapid shortening contractions, the average discharge rate was approximately 75 action potentials per second before training, but after training, this increased to 105 or so. So what this means then is that the greater rate of force development after 12 weeks of speed training was due to an increase in motor unit discharge rates. The speed training enabled motor neurons to discharge action potentials more quickly. So now to the second example for how muscle activation can influence the force exerted by muscle. And this is to talk about how it can be depressed during lengthening contractions. Muscle physiologists often characterize the mechanical properties of muscle by using isokinetic contractions. And this diagram here shows you what an isokinetic contraction involves. So in this example, the foot is attached to a force plate, and the subject is asked to contract the dorsiflexor muscles, one of which is tibialis anterior. When the person contracts this muscle, the foot plate is attached to a motor that can either allow the muscle to shorten and perform a concentric contraction, or lengthen the activated muscle to perform a lengthening or an eccentric contraction. And here on the right are some traces for a shortening contraction. The top trace shows the change in angle. The second trace, the middle trace, shows the torque exerted by the foot, and the third trace shows the EMG activity over the muscle. So So what you see in this measurement here is the muscle was active at a certain length initially, which produced a certain torque. Then the torque motor allowed a shortening of the muscle at a constant speed, and the torque declined a little and the EMG activity increased slightly. So muscle physiologists will perform a series of these isokinetic contractions at different speeds, which means the slope of this line changes. It becomes steeper or less steep and can have a negative slope as well. And when you do this over a range of 14 to 15 speeds, you can produce something called the force velocity or torque velocity curve that looks like this. And what we're seeing here are some data for the knee extensor muscles in healthy adults, not particularly athletically involved. On the y-axis, on the x-axis, the velocity values here correspond to shortening or concentric contractions, whereas the negative velocities refer to lengthening or eccentric contractions. And what you can see is the well-known relationship. If we look at we have two conditions here, one in which the person performed the maximum voluntary contraction at each of these different 14 speeds, and the peak torque was measured, and then the same task was performed, but while the person did that, the muscles received electrical stimulation as indicated by the photograph on the right. And what you see here is the faster the shortening contraction became, the lower the peak torque could be produced. But when the muscle performed a lengthening contraction, under the voluntary contraction condition, the peak torque was slightly greater than isometric, which is zero velocity, and it did not change much with the speed of the lengthening contraction. However, what's important about this comparison is notice the difference between the black and the gray data points. And the interpretation is, with the addition of electrical stimulation, which is an artificial activation of muscle, the interpretation is that when these individuals performed these maximum lengthening contractions, the nervous system was not able to provide enough of an activation signal to elicit the true force capacity of the muscle. So in other words, the activation signal was depressed during lengthening contractions compared with shortening contractions. In contrast, here are some similar data, but these were for 10 elite high jumpers who regularly performed intense plyometric exercises during training. And clearly what you can see is that their training program had taught them to remove or get rid of that depression, activation depression, during lengthening contractions. So voluntary activation for these elite athletes was able to achieve peak force during lengthening contractions. So that's the second example. And the third example about how does muscle activation influence force exerted by muscle is that it can cause a decline in motor function without a loss in muscle strength. So in the USA, the National Institutes of Health has recently released something called the Toolbox. And this is a set of measurements that are used to characterize human health and function across the lifespan. There are 4 domains of assessment: 1, cognition; 2, emotion; the 3rd, motor; and the 4th, sensation. Motor function is assessed with tests of balance, dexterity, endurance, locomotion, and strength. Dexterity is measured with the pegboard test, where the task is to take pegs out of the well here, one at a time, and place them in the hole, and to fill the pegboard as quickly as possible. In the study that I'm going to tell you about, they looked at the pegboard times for young adults, middle-aged adults, and old adults. And here are the characteristics of the subjects who participated in this study. the main point to notice is the average age of the young adults was 26 years, the middle-aged adults was 51 years, and the old adults was 75 years. In addition to measuring pegboard times in this study, they measured the strength of the hand and also something called force steadiness. And these measurements, they were made to try to explain any difference, any age-related difference they observed in the pegboard times. So they measured the force that the index finger, the abduction force that the index finger could exert. They also measured the pinch grip force, and not shown in the diagram, the hand grip force. In addition, they measured something called force steadiness. So let me just take a moment to explain to you what that is. So first, looking at the graph on the left, what you can see is the person was asked to perform 4 submaximal contractions to achieve a target force of either 5%, 20%, 35%, or 50% of maximum. And the target force was displayed on a monitor, and the person was asked to exert a force that matched the target force and to keep the target force as steady as possible. And what you see in the diagram on the left, for each of these target forces, if they were perfectly able to do this, the force at the target should be flat. But it's not flat, it's bouncing around. And the extent to which it bounces around is something we call force steadiness. So we can measure, we can quantify force steadiness as the standard deviation of the force value, or as its coefficient of variation, which is just the normalized standard deviation. And the graph on the right shows a measurement of force steadiness. It shows the coefficient of variation for young adults in the open circles and old adults in the filled-in circles. And what you see is that each of these 4 target forces, the old adults were less steady. So it seems that usually force steadiness declines as a function of age. What's interesting about this measurement of force steadiness, other studies that I'm not going to tell you about, is that force steadiness is an index of cumulative motor unit discharge rate. So it tells us, it provides information about how the involved motor units during a voluntary contraction are being activated. So let me tell you about the results of this pegboard study. So as you might expect, the time to complete the pegboard task was longer for middle-aged adults than young adults, and it was longer for old adults than both middle-aged and young adults. So what they were interested in the study was, based on these strength measurements and these force measurements, could they explain this difference, this age difference in pegboard times? So here are the strength measurements that they made, and they all revealed the same result. There was no difference in strength between the middle-aged adults and the young adults, but the old adults were weaker than the young adults, but not the middle-aged adults. And in force steadiness, the 2 force steadiness measurements here, pinch steadiness and finger steadiness, there was no difference in steadiness between middle-aged adults and young adults, but the old adults were less steady than both the middle-aged and the young adults. So these investigators did a multiple regression analysis to try to predict the variance in the pegboard times based on these secondary measurements. So there were 75 subjects in the study, ranging in age from 19 to 89 years, and the time to complete the pegboard task ranged from 46 to 145 seconds. And they found correlations between pegboard times and these different measurements here: index finger steadiness, grip strength, pinch strength, index finger strength, and pinch steadiness. When they did the multiple regression analysis, however, only 2 statistically significant variables emerged, and these were index finger steadiness and grip strength. And these 2 measures together explained 36% of the variance, a moderate amount of the variance in pegboard times between young, middle-aged, and old adults. And these data indicate that longer pegboard times were associated with weaker grip strength and reduced steadiness. So the longer pegboard times were associated with worse index finger steadiness and weaker hand grip strength, especially for old adults. Time to complete the test of manual dexterity was longer for middle-aged adults than young adults. However, force steadiness and hand steadiness did not differ between middle-aged and young adults. So this leaves us with the question, why were the pegboard times slower for middle-aged adults than young adults? And at the moment, this is an unanswered question. So, with respect to this first question that I've posed, this is what I've told you so far. The characteristics of muscle activation can influence the rate of increase in force, peak force during lengthening contraction, and performance on tests of motor function. And now to the second question, which is how much do changes in muscle activation contribute to strength gains? And I have 4 very brief examples to answer this question. The first one is that strength gains can precede increases in muscle strength. Secondly, increases in strength differ when trained muscles perform different actions. The third example is that training one limb can elicit gains in the untrained contralateral limb. And the fourth example is that the maximal force produced during 1 and 2 leg actions depends on the training history of the individual. So for the first example, about strength gains preceding changes in muscle size, I've chosen to illustrate this with a study that was performed with flywheel training. If you're not familiar with flywheel training, here's an example of a person in a device. This device was designed by Preceding colleagues to be used during a space flight because of the problems of doing different kinds of exercise. And in this exercise here, in which the person is exercising the knee extensor muscles, by contracting the knee extensor muscles, the feet are raised, which raises the cam and is connected by a strap to a flywheel. So in moving the legs up, the flywheel accumulates kinetic energy and it continues to rotate. So now when the legs are fully extended and the person begins to lower the legs, then the rotating flywheel provides a resistance against this. And on the right, the graph shows the force, which was measured down at the strap level here, during the shortening contraction, so beginning from the knees in the flex position here,